Okay, so my idea here is to talk a little bit about the search for new phenomena at LHC and the thing that we learned since the LHC started. Okay, so uh, you can see the slide, right? So I'm on the second slide.
Perfect, we can see it.
Okay. So what do you know about the nature is that we have basically constituents of matter are leptons and quarks, and they are fermions. And we have also four interactions between these particles: strong electromagnetic, weak, and gravitational. Gravity is actually not a part of the so-called standard model. The standard model of particle physics is basically a gauge theory that includes strong electromagnetic and weak interactions. Gravitation still doesn't have a quantum, at least a decent quantum theory and a gauge theory, so this basically let out. But the standard model is, in principle, a very successful theory. It can explain the interaction between quarks and leptons through these particles that are called the mediators. They are bosons, like the gluon, the photon, and the weak bosons. And you can see in this picture that shows that the standard model is a real success in terms of what it can, a prediction that it does. I mean, you predict just in this last decade, you predict and you measure the cross-section for several processes like production of WZs, dibosons, etc. The top quark also was predicted by standard model. And they all agree perfectly within the uncertainties with the standard model prediction. So the standard model is certainly a great theory, and but it's not complete. One of the things about the standard model, if you are not familiar with, is that all the particles, they cannot have mass in the Lagrangian of the standard model because gauge principle will be broken if you put explicitly a mass term in the Lagrangian. So, of course, this is a big problem if you cannot have particle with masses, because we know all the particles have mass besides the photon, most of them have. And so in order to circumvent this problem, the standard model incorporated the so-called Higgs-Broad angular mechanism, in which you define a simple scalar field that permeates the whole universe, and the particles acquire mass interacting with this field. It's a very simple and elegant solution, but we're not quite satisfied with this because although it's what you can call a very economic solution, you introduce this field like, I don't know if you can see the pointer on it. Can you see the pointer going on or not?
Yes, perfect.
Yeah, okay, so you can see this the potential that you introduce is basically one that probably most of you know is a lambda phi to the fourth kind of scalar field. And with that, you are able to give, to have through interaction with the standard model field, you give mass to the weak bosons, and also you can introduce in the Lagrangian Yukawa couplings to the fermions and give mass to all the quarks and leptons and everything. But it's very artificial, the form that you introduce this field. I mean, you just put it by hand in the Lagrangian, and I mean, all the masses are not quite determined. For instance, the mass of the fermion depends on the Yukawa couplings, and you have to put it by hand because there's no way that you know the Yukawa couplings. So you basically have to know the mass of the particle first and put the Yukawa coupling by hand. So this is not very, it's sort of artificial. And one thing that also can be a problem for the standard model is that if we include the radiative corrections to the field, to the Higgs field, you can see here the Higgs potential. This first term here, the two first terms is the so-called the classical potential, but you have this other terms that are radiative correction. The most important is this third term that has this B. This B is actually the coupling to the gauge bosons and the fermions, and the most important, of course, is the Yukawa coupling at the top, because the top is the heaviest particle, so it dominates. And the lambda, that's the quartic coupling, is small in the standard model. So basically, you can have this potential going negative. That means it's unbounded, and the standard model can be unstable depending on the masses and the mass of the Higgs boson, of course, because the mass of the Higgs boson also entered this equation. Okay, besides that, the Higgs itself suffers from this radiative correction, and its mass should be on the order of 1 TeV. Any mass lower than sort of a TeV and going high, it has to be a fine-tuning problem. And there's also the so-called hierarchy problem. The question is, if the standard model is valid up to the Planck mass, up to the Planck scale, 10 to the 18 and 19 GeV, why are the particles are on the TeV scale? Why is this gap between the physics of the TeV scale and the grand unification? So this is another thing that the standard model doesn't even consider. Besides that, of course, there's the problem of the matter and antimatter in the universe that in principle should be equal if you believe in the Big Bang. Some don't believe in the Big Bang, but it doesn't matter. In any case, there should be quantities of matter and antimatter in the universe should be the same. And CP violation is the only way that the standard model can account for a difference between matter and antimatter. But CP violation in the standard model is so small that it cannot account for that. Also, there is this thing that we, by lack of a good name, we call dark matter, which some matter that believed to be have only weak interaction, because the only way that you can actually perceive this matter is when you look, for instance, in this picture at the cluster of galaxies. You see the mass of the cluster calculated by the gravitational lensing is not the same as you estimate by just the light coming from the galaxy. So it seems to have some missing matter here. And in this dark matter is not compatible with any particles that the standard model has, not even neutrinos. So it could be some other kind of particles, like SUSY particles or anything. There's also neutrino oscillations. Neutrinos need to have mass because you see neutrino oscillations both in the atmosphere. When you have a cosmic ray, you produce mu neutrinos, and when you detect them, sometimes they change flavor for other species of neutrinos. Also, the solar neutrinos also change when they in the way to Earth. So, but neutrinos, they don't have a Yukawa term in the standard model Lagrangian. So they, the neutrino mass implies that you need some physics beyond the current standard model. So how do you solve this problem? Of course, there's a lot of potential candidates to extend the standard model in order to try to solve these problems. Supersymmetry is one of the best candidates because it solves many of the standard model problems, like the Higgs mass that can be stabilized by the presence of fermions and bosons in the same quantity. So you don't have these loops that cause the running of the Higgs mass compensate if you have equal number of fermions and bosons. Of course, none of this this also presents a problem because for that to happen, you need a whole bunch of other particles, the superparticles, the supersymmetric particles, and none of those particles have been seen up to now. So we don't know if supersymmetry is true until we find those particles. Some other models that have been proposed, like extra dimensions. In these models, the gravity becomes strong at the weak scale, so you have an unification of the electric scale. But for that, also there has to be there are several models that predict this, and effects like presence of massive gravitons, Kaluza-Klein resonances, all of those things have been predicted by these theories, and none of those processes have been seen at LHC up to now. So if this looks confusing, the solution that we have is to study the TeV scale at the LHC. Well, if you don't know what the LHC is right now, you should be going to some other place, not CBPF, because I guess all of you know the LHC, the Large Hadron Collider. It's the largest accelerator and the most powerful up to now. But even being so powerful, a small animal can just destroy it, like it happened last week. Anyway, I mean this week, but it can accelerate protons up to energy of right now we are at the 6.5 TeV per beam. So the collision happens in a center of mass energy of 13 TeV, and probably in a couple of years they might try to go to 14 TeV. And well, the LHC has these 4 large experiments. CBPF participates in 2 of them, CMS and LHCb. There's also the Atlas and the Alice experiments. Now, the detectors that have the most dominant programs for beyond the study the standard model and beyond the standard model are the general purpose detectors, Atlas and CMS. The difference between Atlas and CMS is the Atlas is very big. CMS is very compact, but also they are very similar in the detectors themselves. All of the things that they can do, they are very similar in efficiency to detect photons, leptons, and all those particles. So in some sense, it's good to have 2 detectors that have very high efficiency to detect particles, because you can compare results between 2 experiments, and because you don't want to start jumping around with some discovery that you don't have confirmation for that. So it's a good thing. CMS collaboration is Brazil is included on that, and also a lot of countries around the world. And the CMS detector is a state-of-the-art detector. It has about 200 meters squared of silicon. The inner detectors that are close to the beam are the tracking, and the track is composed mostly, basically, of silicon detectors. There is a pixel detector that does the vertexing, that finds the primary and secondary vertex, and the silicon tracker, which is here in the middle, that tracks the particles in the magnetic field and you can measure the momentum of the particles besides the trajectory and momentum of the particles. You have also in green the electromagnetic calorimeter to measure energy for photons and electrons, and in yellow, hadronic calorimeter to measure the energy, the total energy of particles that have strong interaction, the hadrons, like the proton, neutron, and other particles. And in the outer layer of CMS, you have the muon detectors, that the only particles in principle that can leave all of the interior of CMS and reach this outside are muons, because they can traverse a good fraction of material. So this is just to show a detail of a cut of the CMS detector. Unfortunately, I was trying to put this picture in the other computer because there is an animation that goes on with this picture, but it doesn't work on this Macintosh here. So, but the photons, basically, the particles that stop at the electromagnetic calorimeter in green, the photons and electrons, they are absorbed by the calorimeter, and you can measure the energy. In yellow, you have the hadronic calorimeter, so particles like protons and neutrons, they traverse the detector and are stopped by this detector, and you can measure the energy there. The muons are the only particle that can go all the way down on the muon chambers up here, and they can actually leave the detector, and so you don't contain them in the detector. Of course, there is also neutrinos that neutrinos can escape the detector, and usually you only have a measurement of neutrinos using the momentum balance on the whole detector, and you can see missing energy, and this is an indication of neutrinos in the detector. So when we're looking for new phenomena, one of the first things that we do is looking for resonances. So like we did in the past, when we look for all these particles here in the dimuon mass, like the J psi, the upsilon, and the Z, for instance, the dimuon mass can be a sign of new physics if you find some resonance at a higher mass. Of course, the Higgs boson was discovered, for instance, in this picture. This one another picture that we found the Higgs boson in this channel, in the muon channel. So in many of the beyond standard model scenarios, like supersymmetry and the theories with composites, etc., you have some additional gauge bosons, and they appear in mass spectrum like resonance. Could appear, for instance, a Z prime could appear here in the spectrum, like in the dimuon spectrum or diphoton spectrum. And of course, there is also substitutive particles like gluinos and other particles can appear also as resonances. So, for instance, looking for CMS and Atlas looked for resonances in the top and bottom mass. For instance, one could see in this channel if there is a pattern of the W boson or W prime that could decay in the top and bottom in the bottom quark. You could see it as an excess in the mass plot of top bottom mass. So this is in the left side here. You see the result for W prime in the semi-leptonic channel where the W decays into a lepton and neutrino, and on the right side the all hadronic channels where W decay to quarks. So the dotted part of the histogram here represents what to expect from a W prime of 1.8 up to 3 TeV in mass. And you can see there's no indication, real indication of the presence of this particle in both channels. So in that way, usually what we do when you don't see a signal, you put some kind of limit in the cross section of the production of this particle, cross section and the mass of this hypothetical particle. Again, dark matter is also something that we search at the LHC. There are several ways for looking for dark matter. The direct approach is just looking for the interaction of the dark matter with the normal matter. For instance, a dark matter particle can collide with a nucleon in some detector, and you can see the recoil of the nucleon. That's the approach used by this experiment like CDMS, Xenon, and Lux. The indirect search is something you just look for the annihilation of the dark matter particles. That's the thing that's done usually by the satellites like Fermi and AMS that's on the International Space Station. At LHC, we try to look for dark matter produced in the interaction of the standard model particle, producing a pair of dark matter particles. In principle, that's a way that you could be able to see those particles. You estimate the cross section for the production of dark matter particle using usually some kind of effective field theory where you have the estimation of the cross section based on some scale parameter that you use to calculate this vertex of the interaction in the standard model and dark matter particles. So one of the things that you can look for instance, in the dark matter production is the production of either a single jet or a gauge boson recoil against the production of dark matter particles. So you have monojets, production of monotops, or W or Z's or other particles that recoil against the production of dark matter. Of course, as the dark matter has only weak interaction, like the neutrino, it escapes the detection. So the evidence that you search in the detector is the production of one of these standard model particles, jets, photons, W's, etc., recoiling against a missing ET, which is the indication of the production of dark matter. So you can see here the calculated cross-section time branch ratio for the production of a dark matter particle according to the mass of it. This has been calculated for the 13 TeV run. So as you can see, the cross section as the mass goes up, it goes down because of the kinematic reach of the LHC. So also the production of supersymmetric particles in the standard model, I mean in the LHC, will be through the collision of quarks and gluons producing gluinos as quarks. In SUSY, usually if you have R parity conservation, the lightest supersymmetric particle should be stable, which in principle could be the neutralino here. So this particle have weak interaction and escape undetected. So you have also missing ET, missing transverse energy in a detector. the problem with all the searches is obviously that neutrinos also produce missing ET. So most of the background comes from standard model production where you have neutrinos. So it's very difficult for in case to see this kinds of signatures because you have a large standard model background. But in any case, we look for the presence of production of gluinos as quarks using using jets and also in several channels that have the production of Ws and other particles. So you can see here this is from Atlas actually. This is a plot for the search for SUSY particles in several channels, including the production of jets and missing ET, and Ws plus missing Ws and jets plus missing ET. And in this picture here, on the right, you can see the limits that are set to the presence of those particles. And the limits are reaching more than 1 TeV in the gluino and neutralino masses. So in summary, you can see here, this is for CMS. We're looking for several beyond the standard model candidates, like for instance, gravitons, leptoquarks, dark matter, etc. And you can see that for some cases, like for instance, compositeness is also something that cannot be excluded. The quarks and even the leptons can be composed of smaller or more fundamental objects. So you look also for compositeness. There's some other thing that can also be other beyond the standard model candidates. For instance, for compositeness, usually you set a limit on the scale of compositeness lambda, and this is already on the order of 14, 17 TeV on the scale of compositeness. So nothing has been seen, so you put a limit on the scale of compositeness. For dark matter, we're reaching a limit on a TeV scale, also for leptoquarks, gravitons, and in a TeV scale also. So in summary, we haven't observed any particles that could be an indication of supersymmetry or extra dimensions. And the standard model is still the only thing that we see. Of course, I cannot forget the Higgs. The Higgs was the thing that gave the biggest propaganda for the LHC, was the discovery of the Higgs in 2012. And since 2012, there's been a great deal of analysis with more data. So this is this picture here are the results from CMS for the final results of CMS for the whole first run of the LHC, including 8 TeV data and 7 TeV data. There's more than 20 inverse femtobarns of data. So now you have a strong signal from both the decay of the Higgs in 2 photons and in 2 Z bosons. And all the measurements are compatible with standard model in a matter of cross section. For instance, in the left side here, you can see the cross section compared to the standard model cross section for several, not only for the diphotons, but also for some of the other processes where you have top ET bar and a Higgs produced in association with top. And in principle, they all agree within the uncertainty with the standard model. So there is basically no indication of beyond the standard model physics, at least in the Higgs sector. And the mass of the Higgs now has been measured with a very high precision. Still, we'll do better than that after this second run of the LHC with the higher statistics that we in principle would have more than 10 times this, in principle, around 10 times the statistic that we had up to now. So the mass of the Higgs is around 125 GeV plus some error. So now we go back to that question. So if we take into account the mass of the top quark that goes into this factor here in the Yukawa coupling, and the mass of the Higgs that goes into the Higgs potential, now we can really calculate how the standard model potential is in at least if you consider, of course, that there is no other physics beyond the standard model up to the unification of, or up to the Planck scale. Because up to now, we didn't observe anything beyond the standard model. So if we start from the principle that the standard model is correct up to the Planck scale, so including the radiative corrections, the potential that we see is more like this part here on the left, where the standard model is sitting on a false vacuum, and the real vacuum will be somewhere near the Planck scale. So the universe, in principle, if the standard model is the correct theory up to the Planck scale, our universe is in a metastable right now. So this picture here at the bottom gives you more or less, because as you can see in the previous slide, the potential depends on the masses of the Higgs boson, the quartic coupling, but the quartic couplings that we see in the standard model is very small. So the two terms that really dominates are the mass of the Higgs and the Yukawa coupling that goes in this term here. So the potential really depends on the top mass and the Higgs mass. And you can see here the region of stability and instability of the standard model. So the pretty picture that you always see, the Mexican hat, if you take into account the current Higgs mass and the top mass, actually this picture is not the one that our universe is. Our universe is like this one here, because from the Higgs mass that we have around 125 and the top mass around 172 in this region here, which is the metastable region. So in principle, our universe can decay to the real vacuum. We are in the false vacuum here, so we can tunnel. There is a probability, of course, of tunneling to the real vacuum. And if we, here in the bottom, you can see some reference that you can look at. And some people have actually gone to the trouble of calculating the probability of tunneling. Of course, this probability is very small, so the tunneling of the universe would be some billions of years. So in principle, you shouldn't be too worried about that the universe will just tunnel out of existence to tomorrow. But well, nobody knows. Okay, so the thing about this the mass of the Higgs boson at the top is that it looks very it looks so close to the limit of stability that some people are really questioning if we got the right picture here. So maybe we are missing something in the Higgs potential, and actually the universe is in a stable region, and just that we don't know. Any question here?
No.
So there has been some people that are questioning the validity of this picture, because with the current masses of the top and the Higgs, we are sitting very close to the boundary of stability. And so, is that just a coincidence, or there's something else that we don't understand about the standard model, and something that can be beyond the standard model? So if you what? I hear someone there.
Yeah, I have a question. Sorry.
Yeah, go ahead.
Yeah, this plot there, bottom left, about the one with the stability. Is it just based on the standard model theory, or does it assume another model or something else? Do you know?
No. In principle, this is just a standard model.
Okay.
So you consider the standard model to be correct up to the Planck scale. Of course, I'm not a specialist on this thing, but I've seen some people trying to include supersymmetry on this picture, and it actually doesn't help that much. So, well, of course, as I said, I'm not a specialist, but the papers I've looked, the supersymmetry wouldn't do much good in this case also. So maybe there's some other thing that can play a role here, but of course, if we had additional gauge bosons, like in the Technicolor or some other things, I don't know about that. I haven't seen this, but they probably could go, but they have to be really massive to go come into play, because you have to overcome the top Yucca coupling. Anyway, so if this is just the picture we have right now, consider the standard model is the correct theory up to the Planck scale. Okay. So and it's really intriguing that we write at the boundary of stability. So that's something that cannot be just a coincidence, or maybe, I don't know, it is a coincidence. Like, for instance, the universe being almost flat is also considered a coincidence when some people say it's not. So it's a lot of speculation, but no one has actually a good answer for that. So some consideration that we can of course put on that. See, so of course we don't know if this is the Higgs boson. Up to now, this particle has behaved like the standard model Higgs boson in all the aspects, but maybe this is the lightest Higgs boson of the SUSY model. We have to see that. If this particle is elementary or composite, we don't know. It could be in some models like Technicolor. This particle could be a technipi or some sort of composite particle, and that, of course, will change the picture completely. And we all believe that has to something else that has to be beyond the standard model, because we have dark matter, we have all these problems. So so the discovery of the Higgs boson is, of course, a great deal, but it's only the beginning of a new phase. So in conclusions, we can say that the standard model is a great and impressive achievement, but there's many questions still open, and there's a lot of development, experimental and theoretical development. And the LHC is our best tool to attack these problems. The LHC has behaved exceptionally, has been working very well, and now you should have around 10 times more events up to 2018. Okay. So I think I'll stop here, and you have questions.
Thank you very much, Gilvan. That was a very nice overview. Thank you. So yeah, are there questions here in the room?
Of course, I don't want to go to a speculation of the 750 GeV thing because it's just a speculation.
Okay.
Everybody has seen that on the Facebook and other places.
Let's see. Sandro, you still online? You have any questions? Then you can use the Q&A button if you have something.
I cannot hear. He goes. He cannot hear.
No, that's an earlier comment. Yeah. So I guess then everybody is happy. Thanks again, Gilvan. Sorry for the technical problems in the beginning.
No, I had that problem also because I had I have this problem with the microphone, and I have to take this Mac, and I'm not used to Macintosh. So I also was completely lost here.
Actually, Gilvan, I have another stupid question because I don't know how that plot is done, the one with the universe stability. But could some cosmological measurements influence on that plot?
In principle, no. I mean, the only thing to enter into this plot is basically this equation here. So that's the potential of the standard model. And so unless you have additional fermions or gauge bosons or some other thing, I don't think. Well, if you have massive gravitons, I don't know if they enter in this thing. I have no idea, but maybe they could enter in the potential. I don't know. This is something that I really don't know. But you need additional particles going to this equation to change the form of the potential. So if we don't have any additional particles, and that's what this picture is about, because this is just a standard model up to the Planck scale. So if the standard model is correct up to the Planck scale, you don't expect anything else other than this picture here.
I see. Yeah, makes sense. Thanks.
Other questions? I have one concerning the Higgs results you had shown. Is there still room? Is there what's the verdict on the spin of this particle? Is there still room that there?
Well, yes, there's still room for spin 2. There's a small. It's a very small probability, but there's still room for spin 2.
Okay.
It's about let me see the last number that I don't know if I have it here. Let me have well, I don't have this picture here. Let's see. And let me check here. Let me check the other. I had another. Let me just a second. Where is this thing? Okay, let's see. Where's the spin of this thing? I can say by about 90% confidence level is a spin 0 plus, and So the room for spin 0 minus is very small. It's ridiculous small. And spin 2 is there's some room for spin 2. Yeah.
Okay. Okay. Thank you.
So we should. I mean, in principle, we have of course with 13 TV the cross section goes a bit high, but not that much, and of course the backgrounds are still higher. So if you look at the results from last year, you can see that we don't have a big statistic for that in the last run. So maybe at the end of this year we'll have more results with 13 TV, and we will not. I don't think we will answer this question by the end of this year, because we are predicting something like 30 inverse femtobarn this year. But with 300, certainly we will be close to answer this question. And 300 is 2018 or something.
Okay. Good. I think that's been it. If there are no further questions, then thank you again, Gilvan. Thank you everyone for joining, and hope to see you all in 2 weeks then. We'll post the link to this recorded stream later after cutting the video, and then Gilvan, if you want, you can send me also the slides, and I can also upload the slides to the server.
Yeah, sure.
Okay, thank you very much.
Thanks.
Thank you everyone. Have a nice weekend, and yeah, hope to see you soon. Bye bye.
Bye bye.
Bye. Thank you very much.